In Unit 9, we are now in Section 4.4, which is called Conics. It's also referred to as Conic Sections, and we'd like for you to understand where these come from. So first of all, where the math comes from a very famous geometer from Greece named Apollonius of Perga. And he lived in the time around 250 BC, and he is the man that's responsible for all of our knowledge of the mathematics of conics. So conic sections is what you get when you're looking at a double napped cone. So if you look at these two purple cones and how they're stacked on each other at the vertex of each cone, and we're cutting it with the plane. So you see that there's a pink plane there. And so number one is showing how the shape that we get when we have that diagonal plane cutting through the bottom cone, the shape that we see is a parabola. And then if you look at the figure number 2, we have the double nap cone. In the bottom cone, the plane is actually parallel to the plane of the bottom of the cone, the base of the cone. And when that happens and you cut parallel to that base, you end up with a circle. But if you tilt that plane and then cut through the cone, as you see in the upper nap, you end up with an ellipse. And then finally, if you just turn that plane vertical, straight up and down, and you cut straight through so that you cut through both naps of the double napped cone, you end up with a shape called the hyperbola. So a conic section then is the intersection of a plane and a double napped cone. Notice in the figure above that in the formation of the 4 basic conics, the intersecting plane does not pass through the vertex of the cone. So here's the algebra of the conics. We have what's called a general second degree equation. And so if we just look at this from x's and y's, you'll notice that we have leading coefficients capital A, B, C, D, E, and F. And so literally we have as this equation, this equation describes all the math necessary to come up with the standard forms for the conic sections. So that's what these are. As we describe these 4 sections, we'll talk about the locus definition as well of each as the algebraic forms based on the general form above. So we start off with a parabola. In review, the function that is a parabola, and you'll remember, is f of x is equal to ax squared plus bx plus c. It's just a quadratic. And this describes a parabola that is graphed vertically, and it opens up or down in a coordinate plane. So speaking more generally about a parabola is the set of all points, x and y, in a plane that are equidistant from a fixed line, called the directrix, and a fixed point, the focus, not on the line. The vertex is the midpoint between the focus and the directrix, and the axis of the parabola is the line passing through the focus and the vertex. So let me direct your attention to this picture here and describe all of that. You see how D1 is the same as D1 here? Well, that means that here's the line of the directrix. It is equidistant from the point on the parabola, and that point is also the same distance to the focus. So that's what it's describing in the locus definition, that we're the same distance. Now, likewise, the distance that D2 is on the next point is this distance to the directrix, and that distance is the same as the distance from the point to the focus. Now, can I take another point and say the same thing? Yes, I can. So here's a red point right there. I'm going to say that if I went straight to the directrix and got this distance, we'll call this one D3, and go to the focus, that distance to the focal point is also the length D3. That is the locus definition of what a parabola is. Now, if we go on and start to talk about now the standard form of the equation of a parabola, this is what we get. The standard form of the equation of a parabola with a vertex at 0, 0, and a directrix equal to y equals negative p is this. X squared is equal to 4 times p times y. Now, if we take a look at that and look at it this way, there it is, x squared is equal to 4py. And we always talk about this in terms where p is never equal to 0 because that would just, kind of flatten out everything. But let's take a look at this. You see the focal point off the origin, so here's the origin right here. The focal point is p up from the origin. But the directrix is also y equals negative p. So it's the same distance down here, meaning right at the vertex, we're already obeying the idea that the distance from the focal point to the vertex is the same as the vertex to the directrix. And there that is. So if we're going to write it, then we say x squared is equal to 4py. And that p in this case is arbitrary at this point, but we'll get some meaning to it. Now, if we wanted to turn this parabola on its side, we still start with the vertex at the origin, so that's at 0, 0. But look at what we have now. We have y squared is equal to 4px. And so we go p to the right and p to the left. P to the left gives us the directrix, p to the right gives us the focal point. So these are the ideas here as we're trying to come up with the standard form for the equation of a parabola. So in example 1, we're trying to find the focus of the parabola. Well, let's see, we were given that the equation of the parabola is y equals negative 2x squared. And it looks like this, and we can actually calculate some things. So we have to start off with dividing both sides by negative 2. So we're just going to say x squared now, when I divide both sides by negative 2, is equal to y times negative 1 over 2. Isn't that true? Well, we were told that the standard form says that x squared is equal to 4p times y. So doesn't that mean then that this 4p is the same as negative 1/2? So that means then that 4p is equal to negative 1/2. And if I divide both sides by 4, or multiply both sides by 1/4, I get p then is equal to negative 1 over 8. So what we want to do is say that's the focal point. The focal point then, since we have to add that to the vertex, we're just going to say 0, negative 1/8. And that's the focal point. So if you look at the picture, that's exactly what we have. We have the focal point is right there, and it has the coordinates 0, negative 1/8. And that was solved by understanding what the definition of the equation for a parabola is. Okay, let's move on to the next one. Example 2, parabola with a horizontal axis. So if the horizontal axis, meaning that the vertex and the focus are laying on the axis of the parabola, then we must be looking at, the equation where we're talking about y squared is equal to 4px. So write the standard form of the equation of the parabola with vertex at the origin and the focus at 2, 0. Okay, so we know that the focal point is already 2 off from the origin. So we know that P is equal to 2. So 4 times 2 times x is supposed to equal then y squared. And so the equation is going to look like this now. Y squared is equal to 8x. And what is it asking for? Write the standard form of the equation of the parabola with the vertex at the origin. And there it is. Y squared is equal to 8x. So here's a little bit of information here. It's a great thing to talk about this. Parabolas occur in a wide varieties of applications. So for instance, in this picture down in the lower left here talking about a light source and things like that. Let me just read this to you. The resulting surface has the property that all incoming rays parallel to the axis are reflected through the focus of the parabola. This is the principle behind the construction of parabolic mirrors used in reflecting telescopes. Conversely, if the light rays emanating are coming from the focus of a parabolic reflector, that's how a flashlight works. And it's used in flashlights and are all parallel to one another. And so that's why flashlights have such a nice focused form of light. If you look at that picture on the lower right, these are called whisper discs. And whisper discs are basically parabolic shapes that if you are sitting where this person is sitting, it's kind of hard to see them, but they're right located at the focal point of that parabola right there. So if you were sitting on the other side of this disc right here, and talking, you could talk really quietly. And all of the sound emanating from you talking quietly would just go straight and to that other disc and then bounce off that disc and go into the ears of the person at the focal point at the other end. And you can carry on a very quiet conversation over, that looks like maybe could be 40 yards. And no one would be hearing your conversation.